Very good morning to all of you. Let us go for the next lectures on riverbank protections and the control structures. This is the second part of riverbank protections. As we discussed in the last class about river revetment, today we will talk about the spore, permeable spore, impermeable spore, and how we can decide the layout of the spores. Those are the things we will discuss in detail, but however the more design and all the things will not go much details. Like for examples, we are following mostly for the Indian conditions, as you know it, riverbank protections work extensively has been done for many river like Ganga, Brahmaputra, Brahmini, many river we have successfully completed riverbank protections, and we have lot of experience how to protect the river bank or how to understand the river behavior and control and training, which is much earlier 1971 and 2012 report about protections of Majuli Island, which is part of the Brahmaputra rivers on the flood and erosions. That is the part I will cover it. Again, I need to repeat it, we are not going more detailed design components. You can follow any of the Indian standard codes to how to design that part, or you can go more details about this book, which is published in year 2016. So, that is the major aspect what I want to talk about you. Now, I would talk about the many of the times when you have a rivers, you have the very large gradient rivers, and we want to reduce the slope of a channels. So, we want to reduce a slope of channels. So, what we try to create? We create a small structures, okay, like a structures what is there, okay, small creep or the timbers. These are validate for the hilly regions where you have a steep gradient of slope, and if you construct a small drop structures. So, for like here is a timbers or sloping approach like a drop structures, that means slowly you depositions will be there and it can modify the slopes. So, it can reduce the slope of a channel to stabilize the bank, and basically it also does because of the stepwise we have this drop structures which velocity reductions also effective on energy dissipations. So, we can have a very simple structures, okay, log and timbers, okay, drop structures, or you can have a gabion, or you can have a small wires. Okay. This is what we do it when you talk about this. So, basically the efficiency of grade control structure decrease the increasing the stream size. The gabion may be useful constructing where drop structure where adequate filter materials are available. So, basically these are small structures are used as a drop structures to reduce the velocity and start the sedimentations. Okay. That is what is that, and how to design all these things as a drop structures. You can follow any of the textbooks on this, but you can understand it is a very easy concept to know it how we reduce the slope of a stream. Same way, if you want to make it the bank is protected, you can have a concrete walls. Okay. These are okay, where you have a small streams and you want to protect a certain stretch of the river bank. You can think about to have a concrete wall. Okay. So, you can have a backfill, you can have a drain systems, and or you can have a masonry wall with a backfill and concrete things, or you can have a gabion wall. Okay. So, you can have a backfill patterns. So, basically gabions are baskets with a metal meshes, geotextiles are filled with stones, have a wide vessels for the hydraulic structures. Nowadays, gabions play the major roles, and you can have a filter cloth. So, you can have the filter cloth. and this is what you can have a this is typical wall you can construct, it's very large, and here you can have the concrete walls. Okay. These are the basic structures. You can protect a smaller reach, the more vulnerable, because it is quite expensive to have this type of structures where you go about a channels where the depth is more than 5 to 6 meters, then cost will be much larger. And if you go for the next part, if you see that you can have a stone riffraff and the river is flood level is here, you can have a reinforced concrete base with a stem, with a wall cantilever upward of this face. Okay. These are good when we talk about the smaller rivers, as well as you can consider this retaining wall. The cost is so expensive, but this is what is showing it the drain, also it is showing the groundwater tables, okay, how it is there. Or you can have a this reinforced concrete wall like this with having the buttress in the both the sides. Okay. So, we can have a cantilever wall. So, basically the stem is designed to resist the lateral soils and the hydrostatic forces. The soil above the base provides a mass to resist the movement, which is very basic things. Okay. And well stem may be the supported or stiffened by the buttress front of the wall, that is what is here contemplated behind the walls. So, these are the small structures, it is not used for a larger river like Brahmaputra, but smaller streams and you have a vulnerable reach, you can think for this type of protections work. Okay. If you go for the next ones in a smaller case scale, we can have the seat piling wall. Okay. So, we can have a seat piling, this is filling materials, this is the dredged part. So, you have these original bank lines, then you have a cut and fill and you create the seat piles. Okay. So, basically a flexible wall or flexible blockheads we can be seat piling walls normally constructed by the driving the seat piling, that is what we do it. And you can have a encourage the increase the allowable heights. Okay. So, with a flexible cantilevers, if you look at that, you can have anchors and you can have the seat piling things. Okay. And you can do the geotechnical design of the seat piling, what could be the depth and what type of anchoring you should provide and what is the strength of anchoring. Those things you can look it as a geotechnical perspective to design the seat piling, and whether it can have a cut and fill or it can have a anchored wall. Okay. So, it may provide a structural members is buried beyond the zone of active movement within the soil. A rod is connected to that member, tension against the wall. Okay. So, you can design the seat piling wall. Okay. These are small structures we can construct it along a small rivers where we have the much vulnerable stretches. Now, let us come back to the many points we cannot make it the bank protections with the revetment of the walls. Okay. We try to look at the divert the flow from the bank, that is the idea that flow should not come closer to the bank, we can deflect the flow, from the river. So, what we look at that we do a small is a hard points, like if you look at that, if I construct a hard point here, okay, if you look at this is a bank line and if I construct a hard point here, so you can understand it, the flow will be deflected. So, you draw just look at the streamlines, So, flow will deflect it. Because of the deflections of flow, these regions will have a low velocity zone. So, that way we are protecting that bank. So, that is what the deflections are happening at. So, we need to these type of structures, the perturbate into the river we can construct it, which will be the hard point, which will be deflect the streamlines. As the flow streamlines will be deflected these regions will have a low velocity regions. as it is a low velocity regions. So, there will be not bank erosions will happen there. So, we divert the flow, that is what we do it. The structure extend the short distance into the river channel, okay, and it is supplemented with a root sections. Okay. It is not only these hard points, it should have a spore like with a tie back and the topsoils. The majority of the structure is invisible, lower part of considered rock placed under the waters, upper part is covered with the topsoil seeds with native vegetations. We can put it like that with a native vegetations and all. The basic idea is that deflect the flow from this erodible bank, constructing these hard points, which is not much technically. The stones with have a tie backs and you can have a spore, and then in the top you can with the topsoil with the seed you can have the vegetations layers. So, if you look at the next slides which are talking about as a engineering points, we talk about the spore and groins. Okay. Spore or the groins, which is a structure or embankment projected at a fair distance from the bank into the stream to deflect the flowing water from away from the bank. If you look at these structures, if I have a series of spore structures here, series of spore structures, because of that flow will be deflected from this erodible bank. Exactly, if you look at the spore more details, what will happen it, the flow will deteriorate, and here it will create a zone with a low velocity zones. So, that is the reasons it prevents the erosions on the bank. It is used to channelize the wide channels, like for example, if you look at these figures which is having a series of the groins and the spots, you can understand it. This is what the erodible banks, okay. This is what the erodible bank, and there are the different shape of the spore structures are there, different shape of the spore structures are there. These spore have the flow which is deflected by this, and because of this spore, so it is a deflected. So, it is away from this bank. So, this series of the layout of the spore with different size, shape, we can put it. The basic idea is that the deflect this main streamlines the away from the bank, which is the erodible bank. So, the basic idea is to channelize the wide poorly defined stream into well defined channels, and the projected length, if you have impermeable spore, the spore through water cannot pass through it, it can hold to less than 15% of channel width, but in case of permeable spore where through the water can pass through, the sediment can pass through, it can go up to at maximum should be less than the 25%. That means 25% of the length of the rivers we can put the permeable spore, but in case of impermeable spore we can put it at most the 15% of channel width, we can put this type of structure, the spore structures. Now, if you look at more details, here you can understand it because of these spore structures, how this improving the channels. This is a mathematic models theirs. Okay. So, because of these spore structures layouts, and if you look at these velocity vectors, now its river is confined with these, and these are the higher velocity zone, this is the lower velocity zone. So, it is a channelize the river as well as it protect the banks. That is what it happens in this case. There are the spores, okay, and these spores are confined the river with a smaller width as well as it is a protecting this. And if you look at these figures with having the channel bifractions, there are series of the spore structures are there, series of spore structures are there, and because of presence of these structures you can see this velocity zone, this is the higher velocity zone, this is a lower velocity zone. So, it deflect the flow from this zone, it goes through that ones. So, there is very less flow in this branching part, where each the main flow is go through these ones. Also, it has make it the deeper channels. also it makes a differ channel through these ones. So, same way there are a lot of study has been done it with a simulating the turbulent flow with a series of the main river with the natural channels. This is the Mississippi rivers and these two rivers, the hydropower plants, and if you look at velocity distributions and the bed elevations, how varyings are there. So, you can try to understand it how these concepts are there, and you can use these CCH2D models can be simulated for the flow in river, flow divergence to this thing. So, you can understand it how the mathematical models can be help us to know the layout of the spots and what could be the dimensions, what is the length and what will be the layout for that. Now, if you look at the typically a spore is a embankment structures, if you look at that, and there is more details about design of detailed spores is available in IIS code. Here I just graphically I am showing that spore will have a this type of cross sections, if you can understand it will be the embankment and having a stone pitching from front side, upstream sides as well as the downstream side. This embankment could have a width, the top width would be 3 to 6 meters depending upon the 1A routes or 2A routes you are planning it, and you have a high flood levels and you can have a freeboard 1 to 1.5 meters and you can have a stone rebatement in the both the sides, in the both the sides. If you taking a cross section at these points, okay. If you take a cross section at the YY locations, means here you can see that there is a embankment and there is a stone rebatement. It is indicating for us where is the high flood levels, the freeboards, but the downstream of this we should not provide any rebatement because it is not necessary to have a rebatement as you can see it. To protect these the scour hole positions are these look we should have a launching aprons, okay. And that launching apron can have a this thickness, the stone pitching thicknesses are there and it could have a layer wise and the dimensions is given here. So, if you look at that way, the spore is impermeable spore is nothing else, is a embankment is constructed with a stone rebatements using the Gaussian matrix, and to protect these the scour formations you should provide the launching aprons, and that what is the stepwise launching aprons, and that is what will be show you that what conditions are coming it. So, that is what is the basic structures of a design details of a spore. Many of the times we confine the rivers, okay. It is considering having the guide banks, okay. So, if you look at the guide banks, that means basically at the look at the bridge cross section near the end of the approach, we can have a guide bank. So, if you try to look it when you have the guide bonds, okay, both the sides you will have to have a stone riprap and you will have a flow converging to this, okay. So, you will have the scour holes here. To protect this, if you see this, there will be a stone riprap, the high flood levels, and there is a geotechnical design of this embankment considering the top width, considering this freeboard, all we can design it as a guide bonds, okay. More details we do it with having a physical modeling studies or mathematical modelings. The shape of the guide bank, which is you can see it is a quarter ellipse with a major minor axis ratio of 2.5. So, major axis should be approximately parallel to the main flow directions. So, that is what it, and basic the idea is to reduce the flow disturbance like eddies and the cross flow. So, we should try to lay out a guide bond such a way that it should not create the flow disturbance like eddies or the cross flow, okay. So, just trying to trace that you try to look at how we will have the guide bonds, and if you look at the next part which is done it for Majuli River Islands, which is there in the reports, okay, protections of Majuli River Island and erosions in 2012. You can see these rivers, okay, and they want to have a guide bond at these locations, okay. And for that, this physical model set up with a permeable spar, with a guide bond. So, it has been created that physical model set up to try to know it, that how they performs the guide bond, also permeable spar, how they are performing it to diverting the flow and channelizing the flow. That is what, if you look at the figures here, you can see the channels, you can see that island, and you can see this the guide bond, and same things is put in a physical models. Before implementing these structures, we can try to look at what type of things we can do it, because it is a quite expensive for implementing these structures, and as you know it, if you want to implement anything in the structures, you cannot remove immediately. So, that is the reasons. First, a series of physical experiment is to be done it, try to know it, how the flow is happening it, the scour hole formations, the channel deepening is happening it, how effective impermeable or permeable spots, those are things we should look at by measuring this flow, velocity, streamlines with a different flow conditions like 10-year return period plot, 50-year return period plot or 5-year return period plot. So, those things we can conduct the experiment and we can try to understand what is happens it same way we can implement on these rivers. Okay, that is the strategy we followed it for any big river training works. Now, if you look at many of the times we also have a retraders, okay, which is a very simple structures. Okay. So, basically we can create a flow parallels, it is not embankment, we allow these things to overtops it, that is what is that. It is a two of bank slope parallel to the stream used to decrease the velocity behind the structures. So, the basic idea is that as the flow exceeds in that places you will have a flow reductions. The height of the structure usually 1/3 to 2/3 of the stream bank height, okay, that is a retraders. Okay. So, you can see it is a retrader. Some of advantage of these structures are that it can adapt it in wide range of conditions, channel alignment can be improved and usually less costly. So, okay. So, you are not protecting the bank, you are creating a retraders which is a far away from the bank, but which we have a 1/3 to 2/3 height of the stream bank height to, so that it will reduce the velocity in these zones, the erodible zones. Okay. Now, if you look at we also have a, since the dikes are the spots, okay, a stone filled dikes and timbers dikes, and you can see these flow controlling structures what is constructed it, because of that flow is that, and you can see in photographs, okay, the series of dike structures. Okay. Nowadays it is easy to see it, the dike structures, any of the satellite imageries. So, arrangement of piles depending upon the velocity of flow, the quantity of the serpent sediment transport, depth and width of the rivers. Okay. The length of the dike depends upon channel width, the positions related to other dikes and flow depth. The spacing varies 3 to 20 times of the length of the upstream dike, and the wear fence may be used to conjunctions of the pile dikes to collect the more the sediment or reduce the velocity. So, if you look at this way, we also have a very long spar. Actually, basically dikes are very long spar. Okay. Spar is a shorter, so dikes are the longer. Now, let us look at that what are the design approaches which are very qualitative ways of design approach is that we should familiar with overall stream meandering patterns. Whenever you construct the dikes, we should have the knowledge of river meandering patterns as we discussed. That means, it needs to have a thorough morphological studies last 100 years and 200 years, try to know it, what could be the pattern of the stream meandering patterns. Okay. That is the scale we should work it. We should work it that upstream and downstream terminations points. Okay. The downstream terminations points should have existing nick knot of the bank stabilities, and the upstream terminating points should correspond to downstream and adjacent point were deposition zones. Okay. And alignment should be smooth. Okay. There should not be abrupt changes in the radius, then you have the more problems. The signed inspection is there to know about stream characteristics, cross section, bed and bank material and the soil boring. Okay. And there should be always have a two protections is a necessary, and the two protections should be the heavier at the downstream point of the maximum attack. So, these are general guidelines, but detailed design of the dikes also we or the retreads we look it as a geotechnical design or the hydraulic designs conducting at the physical experiments or the mathematical studies for that stretch of the river. I will show one of the case studies what we did it for the Brahmaputra rivers end of this my presentations. So, if you look at that many of the times it is not that way to measure this so expensive work for a larger rivers. What we try to do it a jetty field. Okay. The basic idea of the jetty field it is a just a wear mass. Basic idea is that to add a roughness or the reduce the velocity in the flow on the bank or the channels on a selected path. As it reduce the velocity, and if I have a lot of sediment loads, then the sedimentations can start it, the depositions can start it. So, adding the roughness it reduce the velocity, protect the bank from the erosions, and if it is effective if debris carried by the stream. If the streams having a lot of debris and these debris can plug up it here, and that what it gives additional resistance, and that what make it the sedimentations if you have a lot of sediment concentrations flowing over that. It stabilize the meandering river. It is necessary to have a jetty field in both the side of the river to prevent the chort across the point walls. If you look at same concept, design approach specification of jetties, if you can see that jetty fields looking from the satellite data, you can see the jetty fields. Okay. So, the basically it is a steel jacks together with the cables. Okay. So, the jacks are divided the basic triangular frames tied with together with a tetrahedron frames. Tetrahedrons are placed parallel to the embankment, and the cable together with the end of the cables anchored to the bank. Both the lateral longitudinal row of jacks are used to make the jetty field. So, we do not put it a single jetty, there could be a series of the jetty field. We can put it lateral will have a angle like this, spacing varies depending upon the debris and sediment. So, you can see it the jetty fields which is that steel jacks, but still it is a costly. Okay. River like Brahmaputra or where we want to stabilize the river for certain years, we cannot go for a steel jacks with the cables which is followed in US Association of Civil Engineering 1963 with having a jetty field and the vegetations of Rio Grande jetty systems. That is what you can see in the photographs. That is what not will be possible like country like India. So, what we do it, we do a very simple concept which is called the Procopine, low cost permeable spar implemented in Brahmaputra rivers or the some of other smaller rivers. So, we can have the RCC Procopines, okay, same concept, okay, which is a stables can be laid at the site, and you can see the photograph of RCC Procopines, the dumping of the RCC Procopine. And we can create a Procopine spar. So, you can see the top layout, okay, the top layout of the Procopines. So, it can have a anchoring, and you can have a series of Procopine structures with anchoring. Okay. So, that way you can create a field, and this is your embankments. Okay. So, you can anchor it, and it is the flow directions, and you can try to look it work as the field, Procopine spar field. So, because of a series of the Procopine structures we put it, and that Procopine structures is reduce the velocity, and that reductions of the velocities help us to do the sedimentations, and that's the sedimentations. Because of that, this bank is protected as well as channel also divert from these places. Now, if you look at other one is a smaller structure is called the bands. Okay. If you look at these photographs, you can understand it's the band systems. Okay. You can look at these structures. The basic idea is the same thing, flow away from the eroding bank lines. Okay. And it is directed away from the eroding bank. End of the dikes are subject to a local scour, that is what you have to look at. So, these are the band field, and it is the flow which is divert from that. It can have a rock or erosion resistance materials. It can design water surface elevations. Appropriate allowance should be made to loss of the dikes material into the scour holes, and side slope can be provided. So, just you look at these are the smaller structures which is also implemented in Kosi river in Nepal. If you look at these small structures can divert the flow away from the eroding bank lines, and that is what is create the field. The flow streamlines will go like this, okay, it will not attack here. So, this type of structures also put it in river bank to divert the flow. Okay. This is good for a smaller rivers where we can have a flow diversions like this. No doubt that is called bandway weirs. Okay. This is the last layout what I am talking about you. You can see these band weirs, okay, which is US Association of Civil Engineering are prepare the guidelines to prepare this type of structures, dumping of this with the slope in a band. Idea is that loosely located the navigation channel band, the weirs are typically built with 4 to 14 weirs per band, okay, and designed to control near bed the flow velocity and which reduce the secondary flow, and water is directed away from the outer banks. That is what it happens. It is the same structures, but here is a cost effectiveness because of a small structures we put it as a weir, as you have seen this thing which help us to this more design guidelines and all. You can look at bandway weirs which is there in USA crop of armies and all. Before concluding, I am to show you that one morphology studies what we have done for the Brahmaputra rivers. Basic idea is to know it using the mathematical models whether we can predict the short term morphology of Brahmaputra rivers with or without river training works. So, the basic idea is that using river modeling works, can it's okay for to predict the braided river morphologies, and basic objective is that to get a navigable flow depth, because there is a no the guidelines for a braided river systems, how you have to put the ground fields and physical modelings as it is you know it is having the scale effect, it has a steady state flow conditions or the high cost. Okay. Both the things you know it very well. Now, if you look at this river stretch which is here, okay, is a middle part of the Brahmaputra rivers about 13 kilometers. We use the satellite data, you use the river models, and we try to collect the field data and satellite data to validate this, the prediction of morphology, the hydrodynamic and the beds are they correct. Okay. Is it acceptable by using the simulations models which is having the upstream boundary condition, downstream boundary conditions, and more details are there in the Journal of Hydraulic Engineering. Okay. That is what you can cross refer it. Now, if you look it, it is a quite interesting study and challenging study we did it. These are the survey transect, and each transect we measure the velocity, flow depth, and so this is showing it in a how the bar positions with a 2006 pre-monsoon, 2007 post-monsoon within the year. Okay. How the things has changed. The polygons are the centers and village representing that extent in 2006 impose of December 2007. Okay. So, that much of morphology change is there in centers and all, and we are fitting this data into the two-dimensional hydrodynamic models with a sediment transport. So, if you look at that, we try to predict the thallic lines. Okay. So, if you look at that simulated versus observed, the thallic line prediction is quite enough, okay, bifraction points and this. The same way, if you can look at simulated versus observed, how these conditions has changed, okay, and how the predictions are there with a morphological cases 2007 pre-flood seasons to 2008 the post-flood seasons, how the best map with a satellite data, we just compare it whatever we predict it, how accurate they are. So, that way if you look at next part, look at the velocity ranges from 1 to 2 meter per second, the simulated velocity within the range, but there will be scatter, that there is an uncertainty in velocity measurement in the field. Also the river models what we consider the turbulent structures and all, there is certain degree of uncertainty, and that is the reasons you can have the scatter plot. But more or less if you look at the range of the velocity predictions are fairly good, but in case of the flow depth, I think it is quite interesting. This flow depth is considered much accurately, even if in a braided rivers, with if you look at the observed and the simulated part. Observed are the dots points, distance along these cross sections, okay, and the velocity if you look at which is varies from 1.5 to 2 meters, morely it is following that trend. Now, if you look at the river cross sections, this is what we have observed is a solid lines, and the circulars is a predicting things. I think it's a predicting very well, and these are the cases, and this is the cross sections at different points, and you can see these comparisons of predicted, measured the bed level, upstream, middle and downstream sections. So, for similar way if you look at next part, if I put the river training structures, okay, like there are the primary channels, there are the secondary channels, okay, and if I put the spore structures with a simulated and calibrated models, I can see that how the flow velocity factors are changing it, whether this bank is protected or not, whether it is a closing down these secondary channels or not. All these things we can do a studies once you have a calibrated validated models for a certain stage. So, you can see these velocity vectors and how complexities velocity vectors are there, and that is what showing in the flow depth and velocity vectors. It is showing in the groin fields or the spore field. If you put it in different spore field, how does it behave? So, nowadays it can be done it before implementing the field, we can know it how effective the groin fields. That is the study what we try to do it and summarize this way. So, let us have a concluding these lectures with river control structures, that every users of a river down here should understand that a healthy river is absolutely vital for a healthy economy and healthy tourism industry with Joy Weather Hill. Thank you very much for this lecture.